All right, so we continue with where we stopped last time, and and today's lecture is by far easier because it's sort of we don't have to deal with this horrible theta vacuum anymore because we introduced an axiom and things are going to relax. So as I argued last time, there is a new parameter in the QCD that is comes with this pseudoscalar gluon density that has a non-perturbative manifestations, and if we add A over FA parameter, then it's guaranteed with, of course, a new kinetic term. For the axiom, it's guaranteed that theta gets screened. And that's the essence of the solution. I could reabsorb the theta parameter into A. I cannot change theta, but I can change A. So I'll just write it this way, right? Okay. So now we have argued that this theory is effective, obviously, because it's dimension 5 operator. So it requires UV completion. What's important to understand about the UV completions? Well, we already said that from phenomenology, kind of the indication that FA is 10 to the 9, right, or higher, maybe. So we're not going to build a collider, probably, that goes to 10 to the 9 GeV. So the most important thing that these UV completions exist. Okay, so that's the most important thing. If there would be a difficulty constructing such a model, then you can question this, right? But for axioms, there is a variety of UV completions that go under various names. So the one that I'm going to show you is this type of axiom, and the idea is that we introduce a Pechi-Quinn sector, and that is a fermion with a QCD charge. Let's say it's in fundamental of SU3, and then the complex scalar field phi, and the Lagrangian that I'd like to take is V of so the kinetic terms, obviously, and then minus V of phi star phi. So that's it's invariant under the rephasing, and then minus psi L. Did I write psi L bar psi R? Let's do psi R psi L, and then the scalar field doesn't matter. This matters not at all, actually. Phi plus complex conjugate psi R bar psi L phi star, and this theory has global U1 under which you can rotate, say, the phi field, and this is the QCD charge fermion. Yeah, field. field. And then let's say that psi r doesn't transform, and psi l goes to e to the I alpha phi, psi l, and that is the global symmetry of this Lagrangian, as you can see. And let's have v of phi potential in that form. For example, if we want to stay on the renormalizable level, right, this is then some sort of lambda phi star phi minus v squared. There is a symmetry for the rotating around this circle, and we will assume that in the vacuum, of course, phi goes to v, but absolute value. And then if we take phi to be v plus some Higgs field and the exponent of I a over v, and we substitute it back into this this Lagrangian, and let's retain only the terms that contain a field. We'll end up with psi left, psi right times v. Well, in principle, I could put Yukawa coupling here, right? So I have this I a over fa plus complex conjugate. It is the whole point that is not a it's not a gauge transformation, right? It's a global U1, so there is no gauge anomalies to begin with, and this is the now you can do whatever you can. The idea is to integrate out the fermion, so the fermion has the mass of yv, and we can chirally rotate it if you don't like that part, and the chiral rotation will give you m psi bar psi plus a over fa times g squared over 32 pi squared g dual. Right? So we pick up a coupling to GG dual because this symmetry is, of course, anomalous. Okay. All right. So apart from this this term, that if there would be no QCD axioms, this would still be a derivative term. If I would draw, it would be still a term that possess these shift symmetries. If I draw the diagrams, the perturbative vertex of A to two gluons will vanish if I take the momentum of an axion to 0. Okay, but non-perturbatively it leads to the mass of the axions. Any questions here? Yes. Now, how do we identify this scale? Right. So. Wait a second. I have done some very quick things. So this alpha over v, when we rotate this, we get a over v, and we have to identify v with the scale fa, right? That's that is a new wave, right? So this is not a standard model wave, and this is not the standard model fermion at all. Say it again.
The fermion should be produced at RC, right?
Oh, no, no, no. We're talking about this FA at the scale of 10 to the 9 GeV. Everything below that is excluded by the Axiom physics, right? So we wish it could be produced at LHC, and that was the original Peccei-Quinn model where V was on the order of a TeV or something like that. That is excluded from so many different levels. From beam dump experiment, from kaon physics, absolutely at odds with the stellar processes, huge number of exclusions, right? All right. You test it through the Axiom. There is no other way.
But there are many axioms.
Yeah, absolutely. This is a UV completion. It's not the UV completion. I don't know, right? So this is the simplest UV completion you can construct using just one fermion that becomes very heavy plus the scalar field, right? So this is an example. There are other examples that go under the name of now I have to not DS with DF S Z axioms, and those usually typically play with the 2 Higgs doublet model where this there is a common U1 that rotates phi fields and HU and HD. In my mind, but not in everyone's mind, this UV completion is minimal because it uses standard model and only standard model at low energy, right? Plus you get an axion. This is already requires some extension of the standard model by introducing the second doublet. But if you are a SUSY person, then of course you have a second doublet, right? So the variety of UV completions is possible. Okay, good. Now we're going to have the A is a Goldstone boson, of course, apart from the anomaly, right? This is I already said that it couples to GG dual. If it would be like electromagnetism, A is still a Goldstone boson because this coupling is secretly derivative, right? But because of the QCD effects and instantons, that where A picks up a mass and non-derivative, in principle, non-derivative couplings. The first of them is, for example, the EDM of the neutron, where A enters non-derivatively. Okay? Yes? That is correct, absolutely. So in these models, this is the sort of the end result of this KSVZ model, and there is a coupling to photons that you can come up. I've written it in the last lecture. All the other couplings are generated by the loop levels and by the running of this operator from the high scale to low scale. In principle, of course, GG dual will also, once you start taking matrix elements over the neutron and proton state, will also lead at some level to the coupling of the spin of the neutron and proton to the derivative of the axion field. Yes. That is correct. That's the whole point of the axion, that this is the only source. From the UV theory, this is the only source of non-derivative interactions. And they're non-derivatives only because of this thing gets a non-perturbative contribution in the correlator of GG dual, which we have calculated last time through the chiral rotation in the Lagrangian. And importantly, it's non-zero because eta prime gets a mass from the instantons. This is not related to the weak scale as far as I can see. You're right?
Yes, but you can generate crazy low masses for the axons from starting from high scale.
This is the mass would be exactly zero if not the anomaly, right? So this is I don't know how it's related to the hierarchy problem. It probably contributes at some level to, for example, unification of couplings, because I put in smack in the middle between the gut scale and the weak scale some particles that are charged under SU3. So the slope of the running should change after you cross the Pechi-Quinn scale. Okay, but how it's related to the Higgs hierarchy, I have no idea.
I meant to ask, are there mechanisms where A is not the axiom problem theory? Identify A with some other gate group, and with the Higgs, you assume A is a Higgs that generates a small and that will. But that's not little Higgs because it's quite a bit below the. Yeah.
I'm not sure what you're asking. All right, so. Okay, so now let's have this discussion. So we have done the UV completion. Now I give you 4 examples of theories where psi is some heavy SU3 colored fermion, and you tell me which of these 4 models solves strong CP problem, and what are the expectations for masses of these particles are. So this is a quiz, and it's a multiple choice. So you all did a lot of cultural enrichment. So for me, this multiple choice is the type of problems I have never, ever encountered throughout my whole education, right? Not a single multiple choice. So now I have a possibility to learn how it works. So which one are the axioms? Does it solve strong CP? Here's the possibility: A, B, C, and D. Where this is the Chern-Simons current that I have introduced last time. So what do you have any ideas? So let's. Okay. So yeah, good. All right. So what about A? Is it an axiom?
You have
No. This is all what I have. This is my let's say this is what comes from the UV model, and psi is the some heavy fermion. So M psi is heavy. So I in principle should be integrating it out. Yes or no? Yes. So who thinks it's yes? 1%, 2. Who thinks it's no? It's no. Why it's no? Because it's a derivative of the axion field coupled to the gauge in QCD gauge invariant current. Okay, I can integrate out this fermion. This d mu will stay as stuck to A. Okay. This is not an axiom. So what's MA in this case?
So sorry, it becomes an axiom if it's not derivatively coupled to the dual. So
no, the GG dual. We'll get to it because there's one example here, right? So what's the mass of the axiom here? 0. Very good. So this is a difficult case. So what's here? Is it
so you don't have GG tilde at all?
No, I have theta stuck in front of GG tilde, right? This is the whole thing that I get out of the, let's say, UV theory.
But then, do you have some problem?
Or I have, let's say I have pi over 2 stuck in front of the GG tilde.
But you do have that.
Right, I have a theta term. I have a theta term. The question is, does this theory relax theta to 0? The answer in case A, definitely not.
Okay.
All right?
So n phi is very heavy.
Yes, and psi is heavier than the top quark integrated out. So what's about the B case? All right, we leave B. What's about C case? Because no, it's not. It's the same as this case, right? This if I split this into real and imaginary part for the mass, this is how it will partition. So there is asymmetry here. Okay, so there is a symmetry here. There is rephasing symmetry, but it's anomalous because psi is charged under the QCD. Yes. So the mass here will be the mass of the QCD axion. Okay, the one that has this mq times lambda QCD cube dependence, right? Now, okay. So is this an axion? Yes, and this is the same thing. So we come to this difficult case. Or no, is it not? Is it very difficult or not? It is not difficult to see that this is an expansion of this term, where I retained only the zeroth and the first order in A. Well, you need all terms for the exact U1 symmetry. So, no. Well, what's the mass here for the A? Well, it's not written, so we cannot really calculate it. But it will be on the order of m psi over fa times lambda uv. The mass is not protected here because the diagram of this sort, A psi, generates the mass. Okay? The mass term. Now you can ask the question, what about here? I also have the same vertex here. Does the mass get generated? Well, over here, this diagram that comes from that term gets exactly cancelled by this type of diagram that comes from this term. Okay, that's how it works. So I find that this is very instructive to think about this, because you can sort of sharpen your understanding of what how the axiom will work.
Why B doesn't solve the strong symmetry?
Because there is no shift symmetry here. If you calculate the mass of the physical psi, it will be a square root, and then will be m standing outside, and it will be 1 plus a squared. Okay, so this thing does not possess any shift symmetry. Okay, so if I shift a, this thing changes, right? So this is the clearly just out of the, forget the QCD, out of the dynamics of this heavy psi fermion, there is a breaking of this U1 symmetry. If you try to do the same thing here, you'll get sine squared plus cosine squared, and A dependence will drop out, and that's what the Pechi-Quinn symmetry does to you. Okay.
Because it is like explicitly broken.
Here it's explicitly broken. Yes, so that's no good. Okay, even though it looks very similar. All right. All right, so now I just wanted to say that perhaps the most important part of phenomenology, because it sort of requires very, it's really very difficult to get out of this, is the stellar axion emission, right? So we already had last time that MA was on the order of 6 millielectron volts times FA no, it scales inversely, right? 10 to the 9 GeV over Fa. Okay. So this is much smaller than kT in stars, right? So the processes where you emit axions would occur, and most of them would be of this type of variety: a scattering either on an electron or a nucleus going to, a gamma scattering on an electron to a nucleus going to A, or a Bremsstrahlung type scattering where you emit A, or a Primakov type scattering where the incoming photon emits A scattering on the electrons, or protons, etc. So this is leads to the additional energy losses, and this Primakov type process in particular gives the basically gamma probability of gamma converting to an axion scaling as G A gamma squared times let me just put proportional times T times kappa S squared over 32 pi squared, and kappa S is defined as pretty much 4 pi alpha over T times the number of densities of electrons times the number densities of nuclei weighted with their charges. So this is a very well understood piece of physics that you can calculate rather easily and compare. And okay, so G alpha gamma here is the term in the Lagrangian that is standing in front of the 1/4 G alpha gamma A F mu nu dual. Okay.
So that diagram dominates over the first one. Just
they all depend on different couplings, right? So this depends on the coupling to an electron. This depends on the coupling to an electron, and this depends on this A gamma coupling, right? So this is all very much model dependent. Okay.
So there's going to be a rate for each of these.
That's right. So once you specify the model, you stick to this KSVZ, or you stick to the other one. There's many probably in between, right? So for once your couplings are specified, this whole thing is calculated rather carefully. KT, yes, I can put Boltzmann constant to 1 if that's your objection. Yes, inside the sun, the solar core inside goes to the 1.5 kiloelectron volt temperature, right? Yes, it's inside. Yes. It's clear why the inside more matters than the outside. Okay. Because this is a high-dimensional operator, it pays off to scatter higher energy particles. Okay, and the densities there are really by far the largest. So if I look at the emission from the solar interior, we would have a characteristic spectrum with a sort of maximum around 4 keV, which is actually quite a bit larger than the characteristic temperature of particles inside the sun. This would be obviously, so this is the energy of axions, this is the flux of axions, and this is the Boltzmann tail. in calculating this curve, you forget that there are nuclear reactions. So you just take the whatever solar models with the temperature and density profiles. You use these rates for the emission of axions, and you integrate throughout the solar interior. Axions are so weakly interacting that there is not a chance that they're going to be reabsorbed, right? So the problem is just bleeding energy into the axions coming out of the sun, right? So with this kind of thing, you would get d phi over d, the scale of 6 times 10 to the 10 per centimeter squared per second per keV. For G A gamma in units of 10 to the minus 10 GV inverse squared times some characteristic function that gives this shape. What's normalizing here is obviously the and this E in keVs, okay? So what's normalizing here is the temperature of the solar interior. Okay, so this is all nice, and one can set very stringent limits, not particularly from the sun, but basically from other the cooling the energy losses from other stars. And for the sun, you'd require, because it's the best understood star, you would require that, say, luminosity in axions is less than 10% of the total solar luminosity. If you change that, you will change a lot into the internal structure of the sun, and you will affect the boronate neutrino fluxes that are being measured in the solar neutrino experiments. Okay. So once produced, suppose we have a flux of axions, and then if I introduce somewhere in the lab a magnetic field, I could actually try to see the axions converting or oscillating into photons in the presence of the magnetic field.
So a quick question before that. So
yeah.
Does it also affect star formation, sort of action stuff, or that's not really?
Well, we don't have a very super good theories of star formation, right? So the best constraints come from the best understood stars, right? So the best constraints come from the red giants, because that is a very well understood piece of stellar physics. Somewhat less understood part as supernovae explosions. But if you make the couplings to the axions too big, the general belief is that they would carry away too much energy at the start of the explosion, and the explosion would choke, right? So the supernovae constraints probably should approach as an order of magnitude constraints, right? Because it's not a super precise science, really. And then yes.
Can it be the other way around, to use axioms as a mechanism to blow a supernova?
Well, you would not blow it, but you could have some other particles from the dark sector that actually. The problem with supernovae, as you may know, is that people try to explode them in the computer, and it doesn't quite work, right? So what other particles, not axions, because they're super weakly interacting. So you could have some particles that interact in pairs, some chi particles, like very light, for example, super light dark matter particles or dark radiation particles that provide additional glue for the explosion that retains energy. Then it would be easier to explode type 2 supernovae, core collapse supernovae. Okay. Yes. ISM does not have much energy, right? All right. So this this is heavily researched, and there are nice reviews, in particular by Georg Raffelt. That he even has a book of sort of 400 pages that you can consult, not specifically about axioms, but sort of probing the fundamental physics with stars. Okay. I'll tell you more. So, whenever you try to construct something in the lab that looks for very light particles, that interact somehow with the Stern model, the stellar constraints is your primary concern, because it is. I can only sort of name maybe 2 or 3 or 4 examples where the terrestrial searches can be more sensitive than the energy losses in the stars. Okay, so this is a big competitor of any experimentalist who comes and studies the spin-spin interaction due to the axion exchanges. Well, they're confined to with current sensitivity probing a phase at the level of 10 to the 6 GeV, right? And this is so much in the excluded region that it's hard to get excited about it. Okay. All right, so I'm hopelessly behind time, so I would not do this derivation for you. However, I'll just sketch it. So if you have interaction Lagrangian, which is basically 1/4 A G A gamma F dual, which is the same as A G A gamma EB. So you can have, this is a lab magnetic field, and this is the electric field of the gamma. So if you have some sort of a magnet oriented towards the sun, and the axions with energies of that curve, right, few keV, come in the magnetic field that's oriented this way, they can convert to X-rays, which of course you can detect then. Okay, so this process is really like the neutrino oscillations, and I will just so basically the fields, the axion and X-rays, they go with normal kind of fast oscillating exponent, but there would be basically a 2-dimensional vector flavor, if you like, right, that oscillates. There would be that these are small, slow varying functions of the distance inside the magnetic field, right? And so this the equation that would govern this evolution of this amplitudes, let's say, is really an oscillating equation with term 0, and then IGB over 2, IGB over 2, and the mass of the axion squared over 2 omega of the photon. So this is, you'll don't feel particularly guilty not deriving the oscillation formula, because A, you have seen it in other parts of the physics courses, and B, you will do a lot of that with neutrinos. So everything will be very similar. Here, just write an answer that, oops, no. What do I do? Right. So I'll just write an answer that the probability of converting an axion to a photon is proportional to the sine squared of 2 theta effective, which you can theta effective read by the ratio of this guy to the difference of this. So theta effective is, it's not a theta term now, right? It's a mixing angle. All right, and another factor is, of course, sine squared of L over L oscillation. So L, this is the distance traveled inside the magnet, so it's L ma squared over 4 omega. That's it. So this is a somewhat idealized formula that you can correct for the if there is an absorption of X-ray in your apparatus on the way to the detector. So in the yes.
How is this oscillation actually happening? So the operator we have is A FF dual.
That's correct.
And there's 2 photons in one.
No, wait. There is that's the operator, right? So the FF dual operator is E dot B, right?
Yes.
So let's say in the lab we have only a magnetic field, right? So you put here in magnetic field. This is the electric field of the photon. When
So it's an interaction of the axion coming in and the B field. And
that is correct. That is correct. That precisely gives the mixing, because this would be like omega A vector, right, of the X-ray photon. So so this would give the mixing of A vector with an axion. For the geometry that I have drawn this, I can even forget that A is a vector and treat it as a length here. Okay.
And does A gets some sort of effective mass, like this photon in here?
A itself is massive, so this is the mass of the
photon itself.
The photon itself will get the mass if and only if there is a gas in addition to the magnetic field, because this would be X-ray photons propagating with the keV momentum through the gas that is way above the plasma frequency, and so the plasma frequency will. If there is a gas, this becomes m omega plasma squared over 2 omega. Okay.
But if you diagonalize that entire matrix, you'll still get an effective mass of the photon.
Yes, you will. You will. However, this thing is so small, right? You get a seesaw mass for the photon, which would be proportional to b squared g squared over this. This is tiny. Okay. It would be smaller than any residual gas contribution to omega plasma. So you would not see this dispersion, if that's what you're asking. All right. So now let me say that when mass of the axion goes small, right, then this whole probability becomes proportional to the g squared, b squared, L squared, right? So the right, because this you can expand, and m will cancel.
Small with respect to W.
When you can expand this, right? Small when this becomes so the oscillation length. It's basically physically it's when the oscillation length is larger than the length of your magnet. Okay, so that's the expansion, and then you would see that the sensitivity in such experiments is really set by the coupling. Of course, the smaller it is, the smaller signal you have, by the size of the magnetic field that you can create, and by the sheer geometric size of your magnet, which is very and all squared, because it's a probability, right? So there's no surprises here. So the things that are being done in this respect are the experiments called CAST at CERN, which uses one LHC magnet that was not good for LHC for some reasons. And then this will be maybe a new experiment called EAXO, which is a much bigger and much more expensive experiment. It's somewhat of a sort of sad astronomy with an axion, right? Because this thing sits in the building with no windows, right? And this thing tracks the sun, right? So you point. I mean, some people may think that you are a little. crazy, right? Because you track the sun inside the room, right? So that's what it is. So very same mechanism. Can create anomalous transparency of the universe to TeV gamma rays. This is quite an active field of research in astrophysics. So the idea is that you have a very powerful source of gamma rays. Some blazes are very far out, and then the TeV gamma rays can scatter on extragalactic background light, produce E plus, E minus, and you would lose the gamma rays this way. The idea now that the gamma rays will convert into axions in some magnetic field that is present at the source. The axions propagate and reconvert back into another magnetic field closer to the Earth, and you receive back the TeV gamma rays. So this being some statements that the universe seem to be somewhat overly transparent to the gamma rays, and that's was a justification for axion-like particles. That is, this formula is very sensitive to this mass. So if you put a QCD scale axion mass, that mechanism wouldn't work. It would become too heavy. And then if you switch instead to axion-like particles, you could still have interesting effects. Because you need a possibility to produce E plus, E minus in collision with some electron volt frequency gammas, right? That's the idea. So if you scatter 1 GeV, you probably will not produce just because the center of mass energy would be a square root of the product of two energies, right?
So, by the way, is that effective constant?
This is not theta angle, right? It's a mixing angle.
When do you expect, is that a constant from this speaking?
It depends on what your magnetic field is. If it goes to small value, this thing, the M cancels from here and here, right?
But how would you expect the first side to be that M squared?
No, M squared cancels, right? If M is small, this becomes M to the 4, and this becomes 1 over M to the 4, and that cancels, right?
I think he's saying when theta becomes very large.
Oh, right. Well, one thing I wanted to say, yes, thank you, that this thing is always smaller than 1, because this is like electron volt squared kind of the magnetic fields, right? And this is like 10 to the minus 10 GeV in the denominator. So this is really tiny. So I'm thank you explicitly in the limit of this theta effective is much smaller than 1. Yes, that's a good point. All right. So what else I wanted to say about the axion and axion-like particles? So maybe I'll skip well, I should say a few words about axion dark matter, right? This is now, due to a lack of time, becomes a very cursory discussion. So axion dark matter is a very active field of research. So basically the idea is that indeed your scalar field is governed by the standard sort of no, just m squared a equation, right? So this provides this is the now. Okay, sorry. A here stands for the so this is not a scale factor, right? This is the Axiom field. Okay, and let's call the radius of the universe is r, right? So humble is r dot over r, right? So this is the standard equation. The difference is that, or the kind of the subtlety is that this is all the expressions for the mass of the axiom that I have provided were zero temperature things, right? So in principle, this is ma squared over of t. Okay, so the picture is that if I just naively keep it as let's just do some atrocious thing. I'll say that the mass of the axion as a function of temperature is 0 all the way to the lambda QCD, and then it picks up some normal MA mass, right? So then in that situation, what usually happens is the axion starts oscillating as soon as, well, it should start oscillating as soon as its mass becomes larger than the Hubble friction, right? Because this corresponds to the picture of basically initial displacement of axion sitting at well, in this theta dependent energy, right, carrying some energy, and then when h becomes smaller than ma, the oscillations start, right? So this term, besides everything else, ensures that your energy density of so this is a log of r. This is a log of rho a, that your energy density scales as -3, so that it scales as 1 over r to the cube power, and it kind of stays roughly constant before that, right? The energy density, and this critical point is that h becomes smaller than ma. That's the very basic picture. So if you have some particular interest in this subject, you can have a look at paper by Dine, Fox, and Pierce from 10 years ago or so, and that says that for large FA, this is not a highly innovative paper in the sense that other people have looked at it before, but this is probably a more careful job. So for large FA, you get basically this type of behavior, where this is an initial displacement of the axion field in units of FA, and for medium FA, you get basically 2 times 10 to the 4 FA over 10 to the 16 GV to the power 7/6, and again initial displacement squared. So you notice that this is the energy density today in these axions. Notice that these are large numbers. So if for a large FA, you'd have to tune this theta initial to be small, or as I discussed with one of you last night, have some mechanism for diluting the initial axion energy density at or after QCD phase transition.
Theta is the theta angle.
This is the theta angle, right? I'm having too many thetas here, initial theta angle. This is the, you can see here that roughly maybe FAs at the level of 10 to the 12, GeV would be okay with cold dark matter, with FA on the order of 10 to the 12. Yes. Well. All right. All right. So that this basically the idea is that if it's very large FA, that then the oscillations start after the QCD phase transition, more or less. And if FA is not so large, medium, the important thing is that the mass of the axion changes during the QCD phase transition, and there you get some additional suppression. You don't get this 1/a cube behavior, but you get some suppression, and that's also the reason why the powers here are different. Right? This case is simpler. It's just the oscillation starts after the QCD phase transition, and this scaling you can derive in 3 lines, which I have no time to spare on that. Okay. All right. So
I think he was asking, what's your comparing energy, 10 to 16 GeV? How do you compare FA? You're comparing
the FA sets the mass, right? So the FA sets the mass. The mass sets the Hubble rate at which you can start oscillating. If FA is very large, then you get the oscillations typically after the QCD phase transition.
So is the conclusion of all this that without tuning, the QCD axion is actually not efficient to a dark matter candidate, unless you add in some additional mechanism?
Well, I don't see anything. I don't have any particular personal attachment to 10 to the 16 GeV. If I have a Pechi-Quinn sector at 10 to the 12 GeV, that's
I
fine.
think we need 10 to the 9 GeV to get the right, the strong CP problem.
No. We don't. The strong CP problem is independently solved. It can be a GeV, 10 to the 9 GeV, to whatever, right? It would not be solved if it's gazillions of M Plancks, because the evolution will be so slow that you'd still be stuck to the side of your parabola, right? But that's 10 to the 9 is pushed on you by the stellar energy losses, right? And it's very difficult to model build you out of this, because the thermal processes occur, period, right? That's it. Okay, so I have almost no time left. So another thing that I wanted to estimate with you is this idea that Tali was discussing with you last night, and that was the oscillating A of t in the Milky Way, right? So you can think of the axions as a collection of particles, or in principle you can think of the occupation numbers are so huge that you can think about it as the oscillating field. So with the amplitude that we are about to determine, and the period of oscillation at MA, right? This thing is smeared a little bit by the virial motion of the axions inside the galaxy, right? So now suppose I prepare an experiment that looks for this, and the many ways you can look for it. And one way is to look for an oscillating electric dipole, because this creates a theta effective. Oh, I have too many theta effectives. There's theta of t, right? That is just a times fa, right? Of t. So this thing is obviously related to the to the basically the row of axions, which we have agreed to be 0.3 or 0.4 GeV per cubic centimeter, same numbers as you used with Tracy last night. And that was a row of axions in our neighborhood, and that is at the same time basically 1/2 a amplitude squared ma squared. So if you go through the very elementary algebra, you'll get that basically this amplitude of this oscillations theta 0 would be at a level of 1 over fa ma square root of rho 2, I think. And so what I was calculating last night, you get 4 times 10 to the minus 19. Is it large or small? It's very, very small, right? So the point is that with the constant dipoles, the current experiments probe 10 to the minus 10 domain. Okay, so if you ever going to probe this in the oscillation regime, you better have a good guess about what the frequency is, so that you can possibly build a resonance scheme exploiting this signal oscillating on one and the same mass. Yes?
What is theta? What is the angle of theta? Theta should be A over FA.
A over FA, yes. Thank you. So this is the thing that so axion field oscillates, but let's not forget that its non-derivative couplings lead to the electric dipole moment. So in principle, you can get electric dipole moment that oscillates in this, but unfortunately, the dn that you would get if you remember the numbers that I was getting to you yesterday at the level of 10 to the minus 16 centimeters time e times now this theta 0. So this is way below 10 to the minus 30. So it's 10 to the minus 34 kind of e times centimeters, and that's a super tiny EDM to look for. So this is what I'm trying to say is extremely challenging to make this work. Okay, in experiment. Okay, all right. So now there is one other little piece of physics that I wanted to discuss with you, and this is, and I'll switch to the projector in my next lecture. So now I wanted to discuss with you some what I find to me the most appealing phenomenological, coolest phenomenological consequences of extra light bulbs. So all right, so let's imagine the same Peccei-Quinn sector that we had before. All right, and then introduce yet another one with yet another axiom. Okay, so I take KSVZ and I multiply by 2. Okay, so I have basically in the second copy I will make psi also E&M charged. Besides QCD, I will make it E&M charged with some charge Q psi. Okay. What is the low energy content of this theory? Right? If I have one KSVZ sector, the low energy content would be a QCD axion. Okay. Now, what is going to happen if I have two of these guys, and one has some additional coupling to electromagnetism? Well, you obviously will have two light particles in the spectrum, right? Well, how light? How light are they going to be? Are we going to get two QCD axions or one? So we'll get something like d mu a1 squared plus d mu a2 squared plus, let me write g squared g mu nu dual over 32 pi squared a1 over f1 plus a2 over f2, and then maybe there will be another term that is coming from the QED anomaly, and that would be ff dual and maybe a2 over fa with some coefficient I don't care about. So what's the content of this theory? Is if I forget about the QCD, then there are two massless Goldstone bosons, right? So now I have a QCD. How many massive particles I have in this theory? One, right? So the other one stays exactly massless. However, it can surely couple to electromagnetism, right? Because I just made the sectors slightly differently. So a generic situation that you can have in this case, one QCD axion, one massless ALP, coupled to E and M. All right. What is it good for? Any of our oscillation formulae now are not really valid, right? Because mass is exactly 0. What is it good for? The interesting things appear with this business in cosmology, and in particular with polarization of the cosmic microwave background. So, say it again. No, because it's derivatively coupled, right? If I would be A times F mu nu squared, that would be not good, because I would not be able to maintain the mass of the A to be 0, right? But this one has the mass of A is protected by the shift symmetry. There is absolutely nothing that is bad about this theory. That depends on when and how, if this particle thermalizes and when it thermalizes. If Fa is large, it thermalizes so far out that contribution to an effective will be diluted by the energy dump cascades in the standard model, right? So that's if Fa would be at the weak scale, then yes, you could possibly generate like extra degree of freedom. So the cool stuff that you can have is that suppose you have some fluctuations, very long wavelength fluctuations of some massless field, that, or not necessarily massless, it's just maybe small mass. This is a field I'm trying to picture, and there is a photon that is going through and arriving from point 1 and point 2. So let's say the photon was polarized this way. Okay, when it arrives at point 2, its polarization angle rotates by psi, and this psi is simply given by the difference between the this A2, the initial and the final point divided by this Fa parameter, regardless of what the path it took and what A was doing on the way. And it's no frequency dependence. So this is kind of an optical activity mechanism that the fluctuations of the scalar field will provide. So in this model, if you have, so now what's that? So let's say we have a linearly polarized light. when it arrives to the final destination, even in the lab, right? Its angle would rotate by the difference between the scalar field in the initial and the final point.
So, and the subscript of the A is related to the position of 1 and 2?
The position 1 and 2, right? Yes, yes. Thank you. Point 1 and point 2. Yes, not to these two axioms. So this is point 1 and point 2. All right. So now imagine that we have inflation that creates. I had the massless particle A2, right? This is massless. No. There was a one linear combination, right? One linear combination that remains massless, and let me just take this Lagrangian d mu A squared plus A over FA, FF dual, and no mass. That's this the lowest energy limit of that theory, right? As any scalar field, A would get inflationary fluctuations on that scale. Okay, so if we look, this is us sitting here, and we are looking at the surface of last scattering, where the polarization is generated. We would expect some chaotic fluctuations of the scalar field on all scales. These fluctuations, as I'm sure you're being told, stays frozen outside of the horizon and start relaxing once you get inside the horizon, right? But the point is that this point of where we see it, we can put A equals to 0 without any loss of generality, and this field A over here will tell you how much the polarization turned, right? So in particular, if you take, say, a hot spot on the sky, right? And you take you look at the polarizations, the pattern that it creates. What kind of polarization does it create? Before even we get to the axioms, the normal sort of CMB physics. I'm quizzing you on your cosmology courses. Create the pattern of polarization that is E mode. That's correct. How is it going to be? That's how if you picture the polarization vectors, that's how they will look like. If it's a cold spot, it will be like that. Counterintuitive, because you think that's the sun, right? So it's hot, so should have, but no, it's a cold spot. It looks like that. All right, so now, and I'm adding demos because I'm not careful with drawing. So on top of that, you superimpose random fluctuations of this massless axion field, and this thing starts rotating, right? So the axion field, massless axion, transforms E mode to B mode. Because this was a random fluctuation, EB over a whole sky will be 0 because parity is not broken all over the whole sky. But the BB will be not 0 and will be proportional to EE, roughly, times H inflation over 2 FA, 2 pi FA squared. So this is a mechanism for transferring some of the E mode polarization into the B modes, and it's highly non-Gaussian because I use essentially a Fock correlation, right? So I use the fluctuations of the normal matter scale of fluctuations to generate E modes, and I use fluctuations of the pseudoscalar to optically rotate these things. Okay. if on top of this thing you also have some very small mass to that axion compared to the comparable to the Hubble rate, say today or not that long ago, you would also have a unidirectional evolution of the rotation angle. So you would get things where this whole picture on the sky of the E modes will rotate. That is, if there is a unidirectional evolution, that will break parity and create a pattern. So both things are being looked at with the cosmic microwave background. So this is a mechanism that could lead to the observable B modes with the H inflation being much smaller than 10 to the 14 GeV, which is usually the ones that create R that is observable, right? This is that thing I find extremely cool. So if you look at this is one word I say. If you look at some forcing that, let's say that you have this theory with A times F of dual over FA. This is a small coupling, and then we have the mass of the axion that is proportional to Hubble today. That is 10 to the minus 32 electron volts, A squared, and then that would just mean that A started moving around present epoch, and the current constraints on this angle psi are less than basically 1 degree or 0.01. So with that, you can easily see that the sensitivity to so that say if what do I want to say? So and let's furthermore let's kind of say that this is comparable to the dark energy energy density. This way you get the estimates is that delta A would be on the order of m Planck, and in principle there you have the sensitivity to FA that is maybe 100 times m Planck this way. So through this extremely tiny effects of the rotation of polarization, you can in principle probe massless fields that couple to electromagnetism with 1 over m Planck type couplings, which is by itself is quite remarkable. All right, I'm done for today.
So you're saying that after this will drop like slope is -3?
That's correct.
Oh.
Yeah. I have a question.
Yeah.
So here in this.
All right, I'll start from my.